This is the first video for Chapter 12. It covers how to make confidence intervals for regression coefficients. Last week, we talked about the fact that sample means are random variables, and that the sample mean is used to estimate the mean in a whole population. And we saw that there were two different ways to make confidence intervals for the sample mean. We could either use a formula with the t-distribution, take our sample mean, and then add and subtract t star that cut off the percentage of confidence we're looking for in the middle of our t-distribution, and then multiply that by the standard error. We also saw that we could find a confidence interval of the mean by using the quantiles of the bootstrap or resampling distribution, like we had done in Chapter 5. When a model is fit using sample data, the coefficients in the model are also random variables. Those coefficients are used to estimate the coefficients that would describe the relationship between the variables if we could fit the data using data from the entire population. And because they're based on samples from the population, the coefficients would be different from different random samples. For example, if we look at the cherry blossom 10-mile race, this data comes from all finishers of the 2005 race. And so if we look at the relationship between age, sex, and finishing time, which is called net in the data set, the coefficients when we fit the model to the entire population of all finishers are given here. We can see the intercept is 5,339.16. We've got a coefficient of age of 16.89 and a coefficient for sex equal to negative 726.62. If I fit the model using a random sample of 100 finishers from the race that year, I get a model fit with the coefficients given here. Notice that I use the deal function here to randomly select 100 finishers from that race data set. Now when I repeat this process and choose a different sample of 100 finishers, you can see that my coefficients are somewhat different. Right, so every time I choose a random sample from the population, I'm going to get a different value for each of those coefficients. And also, if you recall, these are not the same values as what we saw when we fit the model to the data from the entire population. So there's a sampling distribution for each coefficient. Sampling distribution is showing us how the coefficients are changing from sample to sample when we take different samples of the same size from the same population. Now to create the sampling distribution, what I did is I used the do function to take many different 1,000 different random samples from that race data, each one of size 100, and for each one I fit this model. Then I'm looking at a histogram of all of the different intercepts from these 1,000 different models. Right, so this is showing how the intercept varies from sample to sample when I take random samples from the population of all finishers of the cherry tree 10-mile race in 2005. Notice that this distribution has its mean 5,340.11, which is very close to the intercept when I fit the data to the population. Similarly, I can look at the sampling distribution for the coefficient for age from 1,000 different random samples of 100 finishers. Again, I get a distribution that's fairly bell-shaped and has its mean close to the population coefficient for age. And again, the coefficient for sex male has its own sampling distribution. So these sampling distributions have common characteristics. One is that they're approximately normal as long as the sample size isn't too small. And the other is that they are centered near the coefficients from fitting the model to the population data. Just as last week we saw two methods to make confidence intervals for the mean, we have two similar types of methods that we will use to make confidence intervals for model coefficients. One approach we can take is using the coefficient plus or minus a t star value from the t distribution times the standard error. When we're working with making confidence intervals for the model coefficients, the number of degrees of freedom are n, the sample size, minus the number of coefficients that are being estimated in the model, and that does include the intercept. Note that for 95% confidence intervals, we can replace t star with 2 as long as the sample size is relatively large and get a reasonable confidence interval. The other thing we can do is we can use quantiles of a bootstrap resampling distribution to give us the confidence interval. The example we're going to look at to illustrate these methods is coming from the Galton data. Remember that Galton's data was looking at heights, and it came from a sample of 898 people living in England in the late 19th century. We are going to focus on understanding variation in height as explained by sex, mother's height, and father's height. So our model is taking the form height equals the intercept b sub 0 plus b1 times the sex equals male indicator variable plus b2 times mother's height plus b3 times father's height plus a residual. So how do we find the standard error for a model coefficient? Well, the way that we're going to do it is by using R to get the regression report. And the way we do this is by using the summary function. So the first thing I need to do is fit the model, which I'm doing here. I've got my model equals the linear model. And then if I use the summary function and then put the name of the model in, the second row of code here, it gives me this regression report, which has a lot of information. Some of it we're not ready to use yet, but we can see that we've got the estimates for my intercept and for each of my coefficients. And it's also giving me the standard error. Now these t values that we have over here, we're going to ignore those for now. Those are not t star values and they're not confidence interval values. Those are relating to hypothesis testing, which we're going to start talking about in the next chapter. But for now, we're using this regression report to find the standard error for each of these different coefficients in our model. So once I have this regression report, if I want to make my confidence interval, I can take my estimate for the coefficient and then add and subtract a margin of error that's equal to the t star value that cuts off the middle percentage I'm looking for as sort of my confidence level times the standard error, which I'm taking from this regression report. So first of all, since I have 898 as my sample size in the Galton data set, and I've estimated 4 coefficients, the intercept plus sex male, mother and father, so that's 4 total things. So I take 898 minus 4, gives me 894 degrees of freedom. Then I figure out the 97.5 percentile for a 95% confidence level. And remember, that is because if I wanted to cut off the middle 95%, I'm going to have 0.025 down here. So this is going to be the 0.975 quantile. Right? So I'm taking the quantile of the t-distribution. That gives me 0.975 in the left, and I'm entering the degrees of freedom, and it gives me my t-star value. So I know my t-star is 1.963. Now, to make a 95% confidence interval for the intercept, I'm taking the estimate for the intercept, adding and subtracting my t-star value, 1.963, times the standard error, which I'm taking off of the regression report, and it gives me a confidence interval that goes from 9.953 up to 20.737. Similarly, I can make a 95% confidence interval for the coefficient for sex male. I'm just taking the estimate that corresponds to sex male, using it as my estimate for my confidence interval, and then taking the standard error corresponding to sex male and using it in place of the standard error in my formula. And I can do the same process to find 95% confidence intervals for the coefficient for mother and for the coefficient for father. So there are my 95% confidence intervals. Now I want to interpret my 95% confidence intervals for the model coefficients. I have to, first of all, remember what my model looks like. Since this includes more than one explanatory variable, remember that as I'm interpreting these, I need to remember that my interpretations are while holding the other variables in the model constant. So, for example, if I'm looking at the 95% confidence interval for the coefficient for sex male, I can say in the population of all people living in England in the late 19th century, for people with the same mother's height and father's height, I'm 95% confident that the mean height of males was between 4.943 and 5.509 inches taller than the mean among females. Remember, I'm talking about the mother's and father's height being the same because when I put those in the model, I have to interpret the coefficient for sex male, assuming that the other two variables are fixed. If I want to interpret the coefficient for mother, I can say that in the population of all people living in England during the late 19th century, for people of the same sex with the same father's height, I'm 95% confident that the mean height increased between 0.261 and 0.383 inches for every extra inch of mother's height. We want to look at how we calculate a confidence interval for the coefficients using the bootstrap method. Here, what we're going to be doing is, remember, the bootstrap resamples the sample data. So key step here is to be resampling the data in the original sample. In order to do many trials to create a bootstrap or resampling distribution, we need to do the do 1000. And then every time I'm taking a sample, I am fitting this linear model, modeling height as a linear function of sex plus mother plus father. And then if I use the confidence function, it gives me up these confidence intervals. Now we're not going to worry about this part down here at this point, but what we can see is here, it's giving us the lower and upper limits of a 95% confidence interval for the intercept, for sex male, for mother, and for father, and we've got the lower and upper limits. We can pull right off of the report. So, for example, if I wanted to make my 95% confidence interval for the coefficient for sex male, my lower limit is 4.957 rounded to 3 decimal places, and my upper limit coming from here would be 5.508. And comparing the results from the two different methods, we can see that the confidence intervals we get from using the t-distribution, which are here, and the 95% confidence we get from using this bootstrap resampling method are not exactly the same, but they are quite similar. And that's really what we'd like to see. We'd like to see that if we have two reasonable ways of making confidence intervals, that they give us relatively consistent results, and here they do. Remember also that because this bootstrap resampling method uses that random process of resampling from the data, if you calculate those confidence intervals, you're going to get slightly different values than I did just because of the random nature of the resampling process. So I want to talk for a minute about things that influence the size of the standard error. The formula for the standard error is extremely complicated, but the key things to understand about it are that it's influenced by the size of the sample, and larger sample sizes will tend to give smaller standard errors. It's also influenced by the size of the residuals, and larger residuals will tend to give larger standard errors. And it's influenced by how much collinearity there is between the variables in the model. The more collinearity between the variables, the larger the standard error would be. And collinearity is referring to including variables in the model that are highly correlated with each other. You remember that from one of our previous chapters. So what this means is if we want to have small standard errors and have precise estimates of these coefficients, then we need to do three things. We need to make sure the sample size is large. We need to try to include model terms that explain a large amount of variation in the response variable, because by doing so, we'll have small residuals. And we also need to avoid including covariates in the model that are strongly correlated with each other. I'm going to talk for a minute about precision and bias. Suppose we're interested in the effect of sex on height. We can think of the target as being the true difference in height between males and females if we were able to remove the effect of all other variables. Precision in our estimates means that the estimates from different random samples will tend to give results that are close to each other. Accurate or unbiased results would be ones where the estimates from different samples are going to be centered around the target. They're going to be not tending to overestimate or underestimate the effect of sex on height. Now, if we look at the targets over here to the left, the one in the top left corner, we can see all of the results are close together from different samples, so that would mean that they're precise, and they're also in the middle of the, centered around the middle of the target, which means they're also accurate or unbiased. Moving over here to the top right corner, we see results that are close together, so they're precise, but since they're off center from the target value, this indicates that they're biased. In the bottom left corner, we see results that are spread quite far apart, so they're not that precise, but they are centered around the target value, which makes them accurate or unbiased. And then in the bottom right corner, we see results that are spread far apart, so they're not precise, and they also are not centered around the target, so they are biased. So confidence intervals give us a measure of precision. Assuming that the model is correct, they tell us how much error is expected due to the nature of random sampling. For any explanatory variable, the coefficient and its associated confidence interval is going to change depending on what other covariates are included in the model. Bias or accuracy depends on whether the model is specified in a way that correctly reflects reality. And it also depends on whether the sample is chosen in a way that is representative of the population that we're trying to summarize. In the next video for Chapter 12, we'll look at confidence intervals for the model value and confidence intervals for the prediction value of an individual. Have a good day.